functions and types. So let's start with a function. Let's remind function is defined as such in mathematics. We often talk about it like it maps from x to y in that case, and this is also how we write it in functional programming languages. For example, let's say we define a function which is called negate. We use the lambda construction. Let's say here we map from v, which is an integer, to minus v. So this is the general notation of a function by using the lambda syntax. We can write it differently, which is like, and what we can see here is that we have the function which maps from the input to the output. So that's basically it. The return type is at the last position of the function signature. And such type signatures are very important in functional programming, and we use them a lot. Next, what seems important here is when we talk about function is what's the scope of variables. We already used it in our example here when we have a function like this. Here the v refers to the v which was introduced in the lambda right in one scope outside. What happens in a slightly more complicated case, let's say we have a global definition, here 5, and then we implement the function. Let's say foo is a function from x to x plus 5. So here, when we execute it, we can call foo with 2, and we will arrive at 7. Of course, here x captures the surrounding scope which contains the variable 5. So this is basically what we see here. The variable 2 in that case refers to the outer scope where 2 is defined, and this is called static scoping. What we often hear in folklore or in functional programming on Stack Overflow and stuff like this, people talk about the closure. Actually, what this means will be revealed in the lecture about theory. However, the term closure is more like an implementation detail of the language instead of a general concept. There are various kinds how to implement functions on a machine. And one is that either function captures all the variables in a separate storage which are accessible in the function, since when we execute the function later, everything which was available at construction time needs to be available again when evaluating the function. There are also other types of scoping. There is a slide on this, but I will keep this for interested readers. So let's do something much more interesting. Let's say we have a function, let's call it crazy, and the function is defined as such. It maps from a value a. Let's say the value a is of type integer. And here, instead of like say, okay, we want to multiply it by 5, we just construct another function of type b in that case, which in turn then returns a plus b. So what happened here? Syntactically, this is kind of in parentheses like this here. So this means this crazy is a value which is actually a function. When it gets the value a, it constructs a function whereby the function returns a plus b. So what we can see here is that a is actually not a part of the arguments here, but it's in the outer lexical scope of the definition, which makes it available here. But the crazy thing here is what happened now. What we can see here is that the function now is an arrow from integer to integer to integer, which means that we somehow arrived at a function of arity 2 because it takes 2 arguments. However, we didn't use a special notation for multiple arguments, but we just returned a function, which is totally legit when we think about functional programming languages where functions can appear at any position. So what we can do now is we can, of course, execute this crazy value here. By what do we need to execute crazy? Well, what we can do here is, let's call it crazy2. We call crazy by applying the argument 2 to the function. What we arrive now is we get a function actually a value crazy2, which happens to be a function from integer to integer. Why is that? So when we applied the 2 here, the 2 went into this position, and what we end up with is a function which computes the addition. So here we removed one of the arguments here, which was integer. We removed it by applying it with the argument, and then we finally arrive at this position. And what we can do now here is we can do crazy3 is, or let's say this is the result. The result is crazy2 applied with 4. And when we execute this, we can see that crazy is a function taking 2 arguments. Crazy2 only takes 1 argument because 1 was applied already, and result is finally the value. Of course, since we all know that we have this different notation for functions by using the lambda or the inline argument definition version, we can also write crazy a little less crazy. We can just write it like this. So again, we can apply the same argument again, and we can just put the b, which is a lambda construction here, like we did it before on this position. So with less crazy2, we arrive at the function definition, which is actually not crazy anymore. So what we have here is we just have a function taking 2 arguments and we get out the addition. However, this function is actually a function which takes a function which takes an argument and creates a function. So what can we see here? What we basically can see here is that when we write the type of this function here, we can see that it's an integer and it returns a function from integer to integer. However, the type signatures are right associative, which means that we can put away those parentheses. So we end up with this definition. And this is actually exactly the same as we have here. However, what we can do now, also with this version, we can do a partial application. Let's say we can apply not crazy with a single argument, let's say 2, and then we get out a function. And since functions can be applied again by juxtaposition, we can write the other argument right behind, and we arrive with the result of an integer. Oh, just need to define everything here, and we arrive with 10. So this is pretty cool actually, because because what we just did is we invented how multi-argument functions can be defined without support for multi-argument functions. So what we can see here is that add2, in that case, where we applied add with an argument 2, is called a partial application. Why is it partial? Because there's the resulting value has still function type, in that case int to int. And this partial application can be stored into variables or passed around like any other value in a functional language. What did we also see? We see that function signatures and their types are right associative, which means that for carried functions, we do not need to write those parentheses. So add in fact is called a carried function because it's actually composed of single argument functions which return functions and so on. So a carried function step by step consumes the inputs by applying the arguments. So those are called carried functions. And what we also see here, that application, which is kind of the opposite of declaring the function, is left associative, which means that instead of applying 2 to add and then 4, we can just write it in juxtaposition. So why is it useful? Actually, it's useful because we will use it a lot, and you can use it for writing shorter code. In the last lecture, we have seen how function composition works. In that case, we again use function composition, and here we use the plus, which is also an operator in F#. We apply it with the argument 1. What happens? We arrive with a function taking an argument, which is an int, and produces another integer. And then we compose this function by using the function composition forward operator with the string function, which converts any value into a string. So here we can map over a list and produce the list of 2, 3, and 4, but as a string. Then you can use it for making shortcuts of complex functions which have many arguments, but you always use the function in such a way that some arguments are the same. This is kind of a toy example here. We create a custom lock function in this complex algorithm which prefixes the output with a particular argument here with this string. So those steps in that case don't need to write the complex algorithm prefix in that case anymore. There will be more intelligent use cases of partial applications and carried functions in the future. However, this is so to speak the very basic. How does this work in other functions? Actually, it does. When we look at when we look at C# code, what we can do actually here in C# we can define a function like, let's say, we have a function from int to int and is called foo. It takes x and performs x times 2. Actually, this should work. Some IntelliSense problems still. And what we can also do is we can create a function which creates a function which takes an integer and maps it to an integer by defining it in such a way that we take the argument of the first argument and then we define another function which is b, which returns a plus b. And this can again be applied applied by using function application, although here we first need to apply it with 1, then we get out a function and we apply it with 2. So next up is higher order functions and types.